Hi, hello, Partik. This is Sprint 2 database implementation and UI-based system validation. Uh, I'm Marco Zapien. I'm the team lead. We have Sai Gubba, Elliot, and Seth Trimberger. And then we're presenting our Sprint 2 implementation for our project, which is the Meta Capstone course. The goal was Sprint 2 was to design and implement a fully functional database system and demonstrate through a user interface. Our focus was ensuring that the system enforces all business rules, prevents invalid or inconsistent data, and supports real-world operations through complete CRUD functionality. Um, from our tech stack, we use Python and Oracle SQL. Our backend is built using Flask, which handles routing, form processing, and application logic. For database connectivity, we use Oracle DB Python driver to connect the Oracle database running on the free PDB1 service. We also use Docker to containerize our application, which allowed us to maintain a consistent development environment and simplify deployment across different systems. On the front end, we use plain HTML and CSS along with uh, Jinja2 templating, which allows us to render data and integrate it with our Flask application. We focus on building a clean and functional interface for interacting with our database. Uh, During the sprint, we implemented our database using SQL with properly defined primary keys, foreign keys, and constraints such as not null, unique, and check. We also ensured referential integrity using on delete and on update rules. In addition, we validate our system by handling edge cases like duplicate entries, invalid references, and deletion conflicts. We apply normalization techniques to ensure data integrity and reduce any redundancies that may occur. Uh, and that's about it for the introduction. And for the Kanban board, um, we got a lot done. We got a majority of the project done. The only three we still have in progress was was mainly reporting what were these called again, Seth?
Reports.
Yeah, reports, I guess. And then but most of like the core logic on like identifying top spenders, table capacity, adding items, payment, entry per or duplicate entry prevention, purging inactive customers, things like that we got done. Um I think yeah, that's about it for the Kanban board. It's
Yep. Hello, my name's Sai, and we're gonna go discuss the validation of our database with normalization. Uh, and let's just go through our normalization analysis. We made sure our every table in our schema satisfies the first normalization form to the fifth normalization form, and I'll just discuss some of the functional dependencies for each table and then step through each normal form. So our first table is the customers table. Uh, the schema is where it has the customer ID as our primary key, as well as the first name and last name of the customer's phone number, which is unique to each customer, and the email, which is also unique to each customer, and the time we created the customer. The functional dependencies are where the customer ID is dependent on the first name, last name, phone number, email, and the time created. The second functional dependency is that the phone number is dependent on the customer ID, first name, last name, email, and the time created. And given that the phone number is unique, it's the candidate key. Our third functional dependency is that the email is dependent upon customer ID, first name, last name, phone number, and the time created. And like the phone number, the email is also unique, so it is a candidate key. And looking through the normal forms, the first normal form is that every column stores a single atomic value, meaning that there's no arrays or repeating groups. The second normal form is that the primary key is a single column, meaning our customer ID. So our partial dependencies are impossible. Our third normal form is that we have no transitive dependencies, meaning that the first name, last name, phone number, email, and the time created, they all depend directly upon the primary key and not on each other. And our BC normal form is that every determinant, which is our customer ID, phone number, and email, given that those three are all unique, they are all candidate keys. So every functional dependency has a super key on its left side. And our fourth and fifth normal forms, we don't have any multi-value dependencies, nor do we have any join dependencies. And each row represents one customer. Uh, and there wasn't really any changes that we needed for the customer table as it was already normalized. Next, we go on to our restaurant tables uh, uh, table. And in this table, our functional dependencies, our first one is the table ID, and that is dependent upon the table number, the capacity, and whether the table is empty or not. And our second functional dependency is that the table number is dependent upon the table ID, the capacity of the table, and whether it is empty. The table number is unique, so it serves as our candidate key. And moving on towards our normal forms, the first normal form shows that the restaurant table is table. All values are atomic. In the second normal form, we have a single column primary key in table ID. So we don't have any partial dependencies. In the third normal form, uh, the capacity and is empty variables, they depend directly upon the table ID and not on each other. So we don't have any transitive dependencies. The BC normal form, uh, both the table ID and table numbers are candidate keys. And the fourth and fifth normal forms, we don't have any multi-valued or joint dependencies. And as a result, we don't have any changes to make to our restaurant tables table. Next, we move on to our menu items table. And our first functional dependency is that the menu item ID, it is dependent upon the item name, its price, the category, and whether that item is available. And going on to the normal forms of this table, the first normal form, all of the values are atomic. And our second normal form is that we have a single column primary key in menu item ID. Our third normal form, we don't have any transitive dependencies as they all depend only on menu item ID. For our BC normal form, the only determinant we have is a menu item ID because it is our primary key. And our fourth and fifth normal forms, we don't have any multi-valued or join dependencies. And as a result, we don't need to make any changes to our menu items table. Next, we have our reservations table. For this table, we have two functional dependencies. Our first functional dependency is that the reservation ID or res ID, it's dependent upon the customer ID, the table ID, the start and end times, the party size, and the status. So our reservations table, it references the customers table and the reservations uh, table. And our second functional dependency is that our primary key is represented as a tuple of the table ID and the start time. And that is dependent upon the reservation ID, the customer ID, the end time, the party size, and the status. And going on towards our normal forms, our first normal form, all values are atomic. For the composite key, for the second normal form, which is the table ID and start time, we need to check if any non-key attribute depends on just the table ID or just a start time alone, which is not the case. The customer ID, end time, party size, and the status, they all require the table ID and the start time together in order to be determined. So that resolves the issue of having partial dependencies. The third normal form is that we don't have any transitive dependencies as the end time does not determine, say, party size or the status, and the status does not determine the customer ID. And in our BC normal form, both the res ID and the composite table ID and start time, they are all candidate keys. And for our fourth and fifth normal forms, we don't have any multi-valued or joined dependencies. And our overall reservations table, we don't need to make any changes. Moving on to our uh, orders table. We only have one functional dependency, and it's that the order ID is dependent upon the customer ID, the order date, the total amount, and the status. So the orders table, it references the customers table. And moving on towards our normal forms, the first normal form is satisfied as we only have atomic values. Second normal form, we only have a single column primary key in order ID. The third normal form, we don't have any transitive dependencies as the customer ID doesn't determine the total amount, the order date doesn't determine status, and all of the other variables, they depend only on the order ID. For BC normal form, the only determinant that we have is order ID, as it is the primary key. And for the fourth and fifth normal forms, we don't have any multi-valued or joined dependencies, so no changes needed for this table. And for our second to last table, we have the order items table. So we only have one functional dependency, which is that the order item ID references the order ID, the menu item ID, the quantity, and the item price. So our order items table, it references the orders table and the menu items table. And for our first normal form, all values are atomic. Second normal form, we have a single column primary key in order item ID. Third normal form, uh, we don't see quantity and item price determine each other, and neither does order ID or menu item ID, so no transitive dependencies there. And for BC normal form, the only determinant is the order item ID as it's the primary key. And for the fourth and fifth normal forms, we don't see any multi-valued or joined dependencies. No changes needed for the order items table. And finally, we are at the payments table, and we have two functional dependencies. The first functional dependency is that the payment ID is dependent upon the order ID, the payment method, the tax amount, total paid, and the payment date. And the second functional dependency is that the order ID is dependent upon the payment ID, the payment method, the tax amount, the total paid, and the payment date. And since the order ID is unique to each order, it is a candidate key. Moving on towards the normal forms, in the first normal form, all values are atomic. Our second normal form is that we have a single column primary key in the payment ID. The third normal form, we don't see the payment method determine the tax amount, nor do we see the total paid determine the payment date. So no transitive dependencies there. And for BC normal form, both the payment ID and the order ID as a tuple, as a composite key, they are both candidate keys as well. And for the fourth and fifth normal forms, we don't see any multi-valued or joined dependencies, and no changes needed there. So in summary, all of our seven tables, they were already in fifth normal form from the initial design that we have. So we don't need to worry about any decompositions or structural changes. We didn't have to make those changes at any stage during normalization. And yeah, moving on towards the database demonstration.
I'm Elliot. I'm going to talk about database demonstration. We have seven tables. Every table has a primary key. For instance, customer ID on customers, table ID on restaurant tables, table, and so on. We also have six foreign keys for referential integrity. For instance, the reservations table, customer ID references customers, The reservations table ID references restaurant tables and so on. The Then we also have not null constraints. Um, Required fields include first name, last name, and phone number on customers. Menu items, item name, price, and category are all not null. On reservations, every field, including start time, end time, party size, and status, is required. We also have unique constraints. Phone, num, and email are unique on customers. No two customers can share a phone or email. Table num is unique on restaurant tables. Order ID is unique on payments, which enforces that each order can be paid once. And we have a composite unique on table ID and start time in reservations to prevent double bookings. We have check constraints. We have several check constraints. We have capacity is greater than 0 on restaurant tables. We have an is empty in seats. We have negative prices to make sure prices aren't negative. Um, we make sure reservations can't end before they start. We make sure the total order amount is greater than 0. We make sure the tax amount is greater than 0 and the total paid is greater than 0. Um, Relationship summary. The overall structure, customers sit at the top. They can have reservations, which also link to restaurant tables, and they can have orders. Orders contain order items, which link to menu items, and orders can have a payment. This gives us a clean parent-child hierarchy with referential integrity at every level. And then, so we'll move on to the UI demonstration here.
All right, so it's already launched, but this is what our little lemon restaurant looks like. So we have the home tab, customer, reservation, orders, order items, payments, and reports. So for example, if we go to home, we can open our customers and you could see all active customers that are already in the database. We can delete them and we just want to store these for a long time just to make sure if they ever come back, they're already in there. So in here, for example, we can add a new customer. So it would be Sai Gubba. And then, so for example, if you try to add this now, it won't let you add it because there's not a valid email address. But now we should add a customer. And now you can see customer 6 has been added. And then doing from that, we can go to our reservation tab. And then we can have you see all the new reservations. So if you want to add a new one, we could do 5. Here you can see all of our current customers that are in there. So let's say Sai's getting one. He has a table for 1, and he's going to start on the 16th at 1 p.m., 1:50 p.m. He's going to end also on the 16th at 3:50 p.m. He's going to have a party size of 1, and he'll have a status of booked. And then in here, you can also update. So let's go back to Sai, and let's say we canceled his reservation. Boom, will be canceled. It'll show up as canceled on there. And then we can move to our ordering tab. And in here, you can see all our current customers that have an open tab with us. So if we go to our order ID, create a 4, our customer of Sai, an order date for the 16th at 1:51 p.m. Total amount, we'll say it's $8, $3. We'll add it. And you can see Sai has been added with a total of $3. And then from there, we can update. And then here you can say, oh, he added something else, so now his total is 11.59. And it should be good there. We can go back to order items. Here we see our current list of order items. So we'll add a new one. So if we customer 5, order 4. Let's say they added some French fries. They added 5 French fries. And then the item price is 4.50. Add item order. You can see order 4 with an ID of 5, ordered 5 French fries at 5.50. And then we can come back here and then you can see and it hasn't updated. That's the next progress is we need to activate when you add an order item, it goes back to the correct order. But for right now, we can go to payment. So we see only two people have current payments. So we can do a payment ID of 3, order for Sai. He's gonna pay with a debit card. Tax amount is gonna be dollar. Total paid will be 12.59. And then his payment date is 16 at 8:52. And you can see he paid. But let's say we notice his card didn't go through, so we can come in through here and we can add more to his total because there's a fee if your card doesn't go through on the first time. And now he got charged an extra $3, which got updated there. And now we can go to our report section. So in here, it will give you the sales by day. So these are backdated from previous tests, but you can see on 321, we sold $20 in revenue. 320, we sold 40. On the 16th, size spent 15.59. The most popular menu items, you can see French fries, grilled salmon, and cheeseburgers. And we can see our best profit margins will be on the French fries. I mean, on the grilled salmon. We can also see our current reservations, how many booked, how many canceled, how many completed we have. And then top customers by spending. You can see who has spent the most with us recently. And this all gets updated as you do more people as throughout. So then if we go back to reservations, we'll work on an update. So let's say he's canceled, but we made a mistake on our end and now he's completed. We'll make him mark him completed and now his order has been completed. And then we can go back to the orders and then we can update John Smith's order here. And we can say customer John Smith actually got a 10% discount because he's our friend. Well, it's not 10%, but you get the math on there. We can go back, save it there. We can also go to reservations. So if we come here, we can see Sarah deleted is canceled. So we can delete their current reservation. We can go back to customers. Sarah will still be there because she's still in our system, but her reservation won't be there. Her order won't be there. And also, if we go back to reports, Sarah has been deleted off here. So as you can see, she hasn't been deleted, but her amount has been deleted. So that's something also we need to fix on the next sprint. We can go through a few things. So let's say you want to add a customer one, but you already have one. So T or 5 and then T5 at gmail.com. So in here, it won't let us because we already have an ID of 1. So that won't do it. Also, if you have a table of 7, if we start a new table of T, and then we copy John's phone number, and then we do T at gmail.com. It also won't work because our phone number requires a unique constraint. And since it's the same phone number, it also won't let us do it. And if we go back to payments, we can go here. We can say if you can see that Sai has already paid. So we cannot add any more to a payment on him. And then if we go back to customers, if we try to delete something, like try to delete Sai, it won't let us delete it because he's already been in our system and he's already paid for stuff. And that's it for the UI on my end.
All right. In Sprint 2, we completed a full database schema with 7 tables, 6 foreign keys, and over 15 constraints. Normalization verification for all tables up to 5th normal form. We have a working Flask web UI with CRUD on all entities. We have 5 report queries with joins and group by. Sample data covering um, realistic scenarios. What went well? Our schema design was solid from the start. We did not need any structural changes during normalization. The Flask framework let us build the UI quickly. Oracle's constraint system automatically catches edge cases with clear error messages. What we'd like to improve, we want to add user-friendly error messages instead of showing raw ORA codes. We'd also like to add client-side input validation, so input data is caught before the form is submitted. Seth, could you go to the conclusion slide, please? For sprint 3, we plan to add stored procedures for common operations like placing an order with automatic total calculation, add triggers, for example, the auto updating total amount on orders when order items change, and search the filter functionality to the UI. We also want to add on delete cascade or set null when appropriate. We also, as we said, want to improve the error handling. And that concludes our Sprint 2 demonstration. Thank you, and God bless you.
Yeah, God bless.
God bless.
Okay, so you can stop the recording.
Yeah.